For lesson number 1, we talked a lot about our classifications of numbers, our subsets. Those were the reals, the rationals and irrationals, whole numbers, counting numbers, and so forth. Today we're looking at expressions, which is when we take the numbers and we throw those variables in with them, and then evaluating those expressions along with combining like terms. So a relatively easier lesson for us. Order of operations. Please excuse my dear Aunt Sally. If we take a look at this one, there's our please, excuse. Multiplication and division occurs at the same time, so we work from left to right. And the same thing with addition and subtraction. They are equals, so to speak. The fact that we just work again left to right. We start with number 1. On your own, let's go ahead and evaluate the expression when x is equal to -2 and y is equal to -4. You know, at this stage in Algebra 2, we have our calculators, which is great. Strongly encourage you, though, as you write this out, to use your parentheses. And when you plug them into your calculator, you need to be careful that you use your parentheses as well, especially when you get to this one here. Technically, for the order of operations, we probably should leave this alone for now. A lot of us are onto the game where we could multiply all 3 of those together in this step, but that's all right. You know, let's do this real quick with our calculators. Just simply plug in -4 squared. No parentheses. What does it give you? -16, is that correct? No. Okay. What's going on there with that? Well, if we look at -16 squared, essentially the only base that we have here is the 16. Your calculator is reading that as -1 times that 16, 4. It's reading just the 4 to the exponent of 2. Okay, so we got to be very careful when we plug that in. It's a common mistake that students make. Kills them on the ACT. They know what they're doing, but they just don't plug it in right. And that's the reason why you're getting -16 for an answer when you do that. When you plug this into the calculator, now you get this answer, what we want. So, be careful as you go about doing that. It is indeed positive 16. If we multiply all of these together, 2 times 2 is 4, times 4 is 16. It's going to be a positive 16. 3 times 16 will get us what? One more time. And we add the 2 together. 64. You guys have been doing this for a number of years. Just be very, very careful when you plug it in. Let's do another one. On your own. There's your expression. We want A to be -2. B is going to be 4. When we look at this, there are parentheses involved here. But notice nothing, nothing, nothing. You know, we can't do anything inside of those. We can't do anything inside of those. But I will bring about this point is there is an imaginary set of parentheses within this expression, and it's right here. When you use the fraction bar, it is understood to be a grouping symbol. So the first thing we really want to do is simplify this numerator, which all of you did. -2 and 4 will get us 2. And we can simplify that if we want to in this step. That is simply 1. So we're good there. Multiplication looks like it's next. -2 and 4 is -8. And now we have this kind of nasty looking expression. What's going on there? What are we essentially doing there? You're adding 2. You're adding +2. I call it the two-stroke method. We don't like the subtraction sign, we change it to addition. Change the sign in front of the number. -8 plus 2 gives -6 plus 1, -5. As we go about doing these, we now start to look at algebraic expressions, and instead of evaluating, we're going to be looking to simplify or collect like terms. So like terms and constant terms, as you can see from this expression here, we have the 5x squared, which is a like term with the 3x squared, simply because it has the same variables, and it also has the exponents that are the same with those variables. Do we have a like term that goes with this one? Nope. And then these guys, the 4 and the -1, are called constant terms. Constant terms do not have variables next to them. And the reason we call them constant is because regardless of what we decide that variable to be, that value is never going to change. You know, this 4 will always remain 4. This 1 will always remain a -1, and so forth. Hence the reason why we call it a constant term. We want to simplify the expression by adding the like terms. There is your expression. How you go about doing it is really up to you. I like the box and circle method where I box the like terms or circle the like terms. Some students really like their highlighters. So if we wanted to, we have this one, and do we have any others that go along with that one? Morgan?
-yx or -6 yx.
Does the order matter? No, because with multiplication we have the freedom to change those orders. X times y is the same thing as y times x. So just be cautious of that. So we do have, 3 minus 6 will get us a -3xy or yx. Either way you want to write it. If we look at the -2x, there's our match right there to get us positive x plus that remaining 4. Number of different ways that you can express this thing. You could, if you wanted to, x minus 3xy plus 4. That is perfectly fine. Eventually we'll get into, with our polynomials, this thing called descending form, where we write it with the highest degree first and then end with our constant if we have it. Example number 5. It's just a different way of looking at a problem when we have the variables with it. A metal worker is using the 4 sheets of metal shown below with their dimensions. They're asking what is the total area of the 4 sheets. Okay, let's start with this first one. It looks like it's an x by 4. What would its area be? Yeah, we're not for sure what the exact amount is, but as soon as they figure out what x is going to be, we'll simply take 4 times x. Area of sheet 2? Yep. Area of sheet 3, 2x. Area of sheet 4, 15x. So you're catching up. What do we want to do with all 4 areas? Add them together. 4 and 6 is 10. 10 and 15 is 25. Plus 2 will get us 27. And really the cool thing about it is because we use the same variable, as soon as they tell us what that x dimension is going to be, we don't have to go back and figure the area for each one of them. We just simply have to plug it in here and take it times 27 and we have it. So there's your example of where else we can use variables. On your own, A, C,